Hello, welcome to my presentation video on photovoltaic installations part 1. My name is Martin Lavachka and in this video I'm going to talk about the trends and benefits of photovoltaics and its background and technology. So let's start with the trends and benefits. PV technology enables electricity to be produced directly from sunlight, which is a source of renewable energy. PV energy is one of the most promising technologies addressing the global challenge of climate degradation and meeting the pressing need for green renewable energy and sustainable development. PV energy production has several benefits. Solar energy is unlimited, is available worldwide, does not emit greenhouse gases or other pollutants during operation, and consumes little or no water. PV panels are silent producers and require little maintenance. In addition, producing energy from the sun reduces the dependence on energy imports and over the long term should improve the security of energy supply and stabilize the cost of electricity generation. Pushed by sustainable energy policies, extensive country engagement, technology development, and cost reduction, today's installed PV capacity is growing rapidly. By 2016, cumulative PV capacity reached 303 gigawatts compared to only 40 gigawatts in 2010. PV installations are usually split into two main categories. The first category is large utility scale PV installations, typically inject all electricity production into the grid, and utility scale PV installations are more cost effective due to their scale. As the number of large utility scale PV installations is growing, the new grid codes require them to support the grid and assure its stability. The second category is commercial and residential installations like rooftops or car parks, where produced energy can be consumed locally or sold back to the grid. These installations represent half of the installed PV capacity today. There are two main options for photovoltaic energy use: exported to the grid and self-consumption. The exporting to the grid option offers a long-term contract with guaranteed rates for exported PV energy. This model was popular in the past because it was supported by a massive subsidized campaign to expand solar energy deployment. With the decrease in PV system costs and the increase in PV installed capacity, feed-in tariff rates have progressively decreased in many countries, becoming even lower than end-user electricity rates. When that is the case, self-consumption becomes more profitable and thus progressively replaces exporting to the grid for residential, commercial, and industrial buildings. As it is shown on the graph, in 2006, an industrial customer in Germany was paid roughly 40 cents per kilowatt hour for selling its PV energy production, buying its electricity at the much lower tariff of around 10 cents per kilowatt hour. Exporting the PV production was financially advantageous and this option was preferred. 10 years later, in 2016, the tariff for selling PV energy was lower than the electricity rate, so self consumption is more profitable. Self consumption is the economic model where the residential, commercial, or industrial entity uses the generated PV electricity to cover its own electricity needs, thus acting as both producer and consumer or prosumer. The solar energy being produced is consumed instantaneously. If the generated PV electricity exceeds the prosumer's consumption, several options exist to give value to the PV production excess. It can be injected into the grid, stored and used indefinite time, or prosumer consumption can be shifted to fit the PV production. Self-consumption is the model promoted and supported today by a growing number of countries because it makes energy consumers active players in the energy transition and contributes to meeting the objective of increasing the share of renewable energy in the energy mix. Prosumers also prefer the self-consumption model for several reasons. It offers or will offer shortly the greatest economic benefits. It allows prosumers to consume their own solar energy. It provides better control of energy bills, and it promises greater future independence from the grid and electricity rate variations. Photovoltaic energy production remains one of the only means of supplying electricity to 2 billion people who currently do not have access to it. This is a massive way of supplying electricity independent of any network. To size these off-grid installations correctly, it is first necessary to identify the required load curve and the number of days where the installation will not be exposed to sunlight to identify how much energy needs to be stored in batteries. This information is used to determine the size and type of batteries required. Then, the surface area of photovoltaic sensors must be calculated to ensure that the batteries can be recharged in the worst case scenario. PV background and technology. This is the ability to transform solar energy into electricity and is achieved by using photovoltaic cells. A PV cell is capable of generating a voltage of between 0.5 volts and 2 volts depending on the material used and a current directly dependent on the surface area. The photovoltaic effect is dependent on two physical values, irradiance and temperature. As irradiance increases, so do the current and power produced by the cell. As the temperature of the cell increases, the output voltage decreases significantly, and the current increases only slightly, so overall the output power decreases. To compare the performance of different cells, the standard has set out standard test conditions for irradiance of 1000 watt per meter squared at 25 degrees. To make it easier to use energy generated by photovoltaic cells, manufacturers offer serial or parallel combinations grouped into panels or modules. These combination of cells enable the voltage and current to be increased. To optimize the characteristic of the modules, these are made up of cells with similar electrical characteristics. Each module providing a voltage of several tens of volts is classified by its power level measured in watt-peak. This relates to the power produced by a surface area of 1 meter squared exposed to irradiation of 1000 watts per meter squared at 25 degrees. However, identical modules may produce different levels of power. Currently, the IEC standard specifies a power variation of plus minus 3%. Modules with a typical power of 160 watt peak include all modules with the power of between 155 watt peak and 165 watt peak. It is therefore necessary to compare their efficiency, which is calculated by dividing their power by 1000 watt per meter squared. For example, for a module of 160 with a surface area of 1.338 meters squared, the peak power is 100 watt peak per meter squared. Therefore, the efficiency of this module is 12%. However, when photovoltaic cells are connected in series, a destructive phenomenon known as the hotspot may occur if one of the cells is partially shaded. These cells will operate as a receiver and the current passing through it may destroy it. To avoid this risk, manufacturers include bypass diodes that bypass damaged cells. Bypass diodes are usually fitted in the junction box behind the module and enable 18 to 22 cells to be shunted depending on the manufacturer. Since there are increasing numbers of PV module manufacturers throughout the world, it is important to consider the various options carefully when choosing equipment. Installers should also ensure the compatibility of the electrical characteristics with the rest of the installation, ensure that they are compliant with the standards, and select suppliers likely to be in business in the long term to ensure that faulty modules can be replaced, as these must be identical to those already installed. This final point is important as installers are responsible for the warranty granted to their clients. Different technologies are currently being used to manufacture photovoltaic generators. These are divided into two categories: crystalline silicon modules and thin film modules. There are two main categories of crystalline silicon modules: monocrystalline modules and multicrystalline modules. Monocrystalline modules are currently best in terms of performance with efficiency of 16 to 18%. They are also more expensive. The efficiency of multicrystalline modules is between 12 and 14%. They are more commonly used, especially in the residential and service sectors. These modules have a service life of more than 20 years. They lose some of their power over time, but continue to produce electricity. Depending on the look required, biglass modules are available with two plates of glass, which make the module semi-transparent. Or Teflon glass modules which are less expensive but completely opaque. Extensive research is currently being carried out on thin film modules, and current efficiency levels of 6 to 8% should increase in coming years. They are cheap and suitable for large areas provided that the surface is not a valuable part of the facility. This category of thin film modules includes several technologies, of which there are three main types: amorphous silicon, cadmium telluride, copper indium selenide. It should be noted that at present we do not yet have 20 years experience of this type of technology, and thus still do not know how these modules will age. In their technical specifications, reputable manufacturers indicate initial and stabilized values. The table on this slide provides a comparative overview of all these technologies. Inverters are devices which convert direct current into alternating current. These are special inverters for photovoltaic power supply. Different types of PV inverters are available. They fulfill three main functions: converts direct current into alternating current in the form required, MPPT function that calculates the operating point on the photovoltaic surface or array that produces the most power in terms of voltage and current. It is also known as the maximum power point tracker. And automatic disconnection from the network function that automatically commands the inverter to switch off and the system to disconnect from the network in the absence of voltage on the electrical network. This protects the inverter and any maintenance staff who may be working on the network. Therefore, in the event of a network failure, the inverter no longer supplies energy to the network, and energy produced by the photovoltaic modules is wasted. Grid interactive systems are nevertheless available which function in backup mode. But batteries need to be installed for this system as well as an additional control panel to ensure that the network is disconnected before supplying their own energy. On this slide, you can see the operating point of a photovoltaic array that produces the most power, also known as the maximum power point tracker. Some multi-MPPT inverters have a double, triple, or quadruple MPPT function. This function enables PV supply to be optimized when the array includes strings facing in different directions. There is, however, a risk of total loss of supply if one inverter is faulty. Nevertheless, it is possible to install one less powerful inverter per string, which is a more expensive solution but increases the overall reliability of the system. Multi-string inverters are also available. These inverters are not necessarily multi-MPPT. The name simply indicates that several strings can be connected to the inverter and then is paralleled inside the inverter. To compare the various appliances, a level of efficiency has been determined based on different operating points simulating the average daily performance of an inverter. This European efficiency is calculated using the following formula. IP protection and temperature parameters are important when choosing an inverter. Almost all manufacturers of inverters offer IP65 inverters that can be installed outdoors. However, this does not mean that they should be installed in full sunlight, as most inverters operate in degraded mode in temperatures over 40 degrees, and thus output power is reduced. Installing inverters outdoors in full sunlight also incurs the risk of premature aging of some of the inverter's components, such as the chemical condensers. This considerably reduces the inverter's service life from 10 years to as few as 5 years. Therefore, it is strongly advised against installing an inverter in a place exposed to the sun, as this will considerably reduce its service life. Photovoltaic installations require special cables and connectors. Since modules are installed outdoors, they are subjected to climatic constraints associated with high voltages caused by the installation of modules in series. Besides being IP protected, the equipment used must also be resistant to UV rays and ozone. It must furthermore display a high level of mechanical resistance and a high level of resistance to extreme variations in temperature. The voltage drop between the PV array and the inverter must be calculated, and this must not exceed 3% for nominal current. The DC cables used should be double insulated single wire cables. Since these are not standardized, cables indicated by the manufacturer as being specifically for PV should be used. In general, photovoltaic modules are supplied with two cables equipped with one male and one female connector. Using these cables, it is possible to connect two modules installed side by side, thus creating a series without any difficulties. The male connector connects to the female connector of the following module, and so on until the required level of direct current is reached. These special connectors with locking systems offer protection if touched while they are disconnected. This protection is necessary since as soon as photovoltaic module is exposed to irradiation, it supplies voltage. If the cables connecting to the modules are handled, they must either first be disconnected or the DC isolator for the DC circuit must be activated at the input to the connection box. It is also possible to use different connectors available on the market. These should be chosen carefully for their quality, contact, and male-female mating to avoid any poor contact which may lead to overheating and destruction. This is the end of the first part of the photovoltaic installation. Thanks for watching.